as promised, we are going to start something completely different today, and actually something that we're going to be talking about for the rest of the semester. We're going to talk about graph theory. This has nothing to do, at least not really, nothing to do with voting or anything like that, so our sort of vaguely political topics are over. Although I'm sure there are things involved. There are some mathematical things that involve graph theory in that also, but we're not going to talk specifically about any of that. By the way, our next exam is 2 weeks from today, just so that you have that in your mind. So we'll do, next week will be another normal week, and then the week after that we'll be getting ready for the test. All right. Anyway, graph theory. So what this is something that you likely did not encounter in high school math. This is not about the graph of a function, which hopefully you all did encounter even before high school. Graph theory is about things like this. I'll just draw a picture. A graph is like this. It's a certain type of sort of mathematical diagram. It's like this. It involves sort of dots connected by lines. That's called a graph. I'm trying to make a specific example of a graph, something like this. You will notice sometimes you can have two lines connecting two dots, like these two dots right here have two lines between them. Sometimes you can have one of your lines that goes back to the same dot. Anyway, this kind of a thing is called a graph, all right? And believe it or not, there are people like research mathematicians who spend their whole life researching graphs. These kinds of things. Actually, one of our math professors here is a graph theorist. This is her jam, is things like this. I actually do a bit of graph theory in my own research. It's actually super interesting and very useful in a lot of situations. So just some simple terminology here. The dots are called vertices. This is the plural. The singular is vertex, right? So the dots are called the vertices of the graph, and the lines are called edges. All right, so a graph consists of a bunch of vertices, some of which are connected by edges. All right, so this graph has 6 vertices and a bunch of edges. I don't know. You can count them if you want to. Right? This is called a graph. What are graphs good for? Actually, a whole lot. I'm gonna try and convince you today, at least, that graphs are actually very useful in the real world. Just some more very basic terminology. Toims, as they say. One thing that ends up being very important in a graph is called the degree of a vertex, and we're going to talk about this all the time. In most useful scenarios when you're talking about graphs, the degree turns out to be important. So the degree of a vertex is the number of edges that touch it. The number of edges touching it. All right, so on my picture up there, it's very easy to tell what is the degree of each of those vertices. Anyone want to tell me what's the degree of this one here? You can show me the fingers if you like. How many edges are touching it? I see some fingers. It's 2. There are 2 edges touching that vertex. So maybe I'll just write. That one's 2. This is also a 2. This up here is also a 2, right? Those are all degree 2. The one up top on the left, I guess, is degree 3. What I'm looking at is how many edges are touching this thing right here. It's degree 3. This one in the middle, sort of, I guess would be 4, because I see 4 different edges going into here. And then this one, here's a slight ambiguity. This one, actually, we count it as degree 3, because sort of when you look at the point, there are sort of 3 things going into it, even though actually 2 of them are technically part of the same edge. This one still counts as degree 3. So the degree of a vertex is the number of edges touching it, and let me just say looped edges count twice. Usually this is not something you have to worry about, but if you do have an edge that's just going from that vertex back to itself, that counts as 2 because it has two ends of an edge meeting that vertex. All right. So this is a very important bit of terminology. Let me just say, I just said this, but looped edges. A looped edge is one it's one that goes from a vertex back to itself, right? Is an edge from a vertex. I'm often going to just write vert from a vert to itself. That's called a looped edge. You all knew what I meant when I said looped edge before anyway. That's the, just to get it in writing. An edge from a vertex looping back to itself. All right, one more bit of terminology. A path. A path. This is something that is important in graphs also. We want to talk about a path through a graph. Just sort of informally speaking, a path would be sort of a way that you can run through the graph from one place to another. So, for instance, if I want to get from this 2 over here to this 3 over here, I can do so along a path. There's actually several paths that do that, but I could, for example, I could go like this, like that. I'll put little arrows along the path. That's a path. That sort of red line there is a path. All right, just to be specific, how we define what a path is, that's what I mean. It's you go from here to here to here to here to here, right? A path is it's a sequence of vertices that are connected by edges. All right. So, for example, if I wanted to be very specific about a path that I'm talking about, here is another picture of a graph, and I'm going to give the vertices names. Oftentimes, you have to give them names if you want to talk about them really specifically. How about this? So this is A, B, C, D, like that. All right. A path is a sequence of vertices connected by edges. So in this graph, C, D, B is a path. All right, and it looks like that, sort of, right? C, D, B, that's a path in that graph. It's a path from C to B, going through D, all right? But for instance, in this same example, A, B, how about sorry, I'm realizing what I wrote on my paper is not the same as what I'm writing on the screen. That's fine. Something like A, B, C, A. This is not a path in this graph. Why not? Because, I mean, if I try to trace along there, you will see A, B, C, A, like that, right? But there is no edge from C to A, so that's actually not allowed in this graph, all right? This is not a path in this graph. It's because there's no edge from C to A, all right? So that, I mean, you can write A, B, C, A, but that doesn't actually make a path in this graph. Yeah?
But just like A, B be a path?
Yeah, A, B is a path, not a terribly interesting one, no offense. But yeah, each edge just kind of by itself makes a path, yeah.
Could it also be like C, D, B, C? Like you're writing A, B, C, A?
C, D, B, C, yeah, that's a path. Yeah, right. Yep. All right. These are all, I hope everybody feels like this is very, very simple terminology here. This is just to get us all on the same page. There's another word, a special word for a path which begins and ends at the same point. That's called a circuit. A circuit is a path beginning and ending at the same point. Or I should say at the same vertex. All right, like for instance, she just said C, D, B, C in that graph up there. This is a circuit. It's a path starting and ending at the same point. All right. I got one last bit of terminology. This one is maybe a little bit more interesting. A graph is connected when, actually I'm going to sort of leave a little blank space here. Connected means sort of the graph is like all in one piece. So if I were to draw an example, like this here is connected. This is connected. Whereas something like this is disconnected because it has like 3 pieces to it. If you consider that as a graph, it's not connected. This is called disconnected. All right. What it means to be connected is sort of everything on your graph is like all in one chunk. It's not in a bunch of different pieces. I would like to try to write a real definition for this, so without using the word chunk or pieces. I don't want to use the word piece either because it's not, I didn't give a definition for what piece means. Anybody have an idea? How could you say this just in terms of the things that we've already, all of the words that we've already used here, without using words like all in one piece or something like that? Because, what do you think? Circuit.
Well, it's all connected, it's all like a circuit.
Yeah, this one is just a circuit, although you could do something like this. That's connected also, but it doesn't really look like a circuit to me, does it? You know what I mean? That's a good idea. Any other ideas? Yeah.
I'd say when every vertex and edge is touching.
Every vertex and edge is touching. Yeah, I'm not sure. Like,
And not like crossing through the middle.
through the middle.
Of the
Not all
concentric
graphs have a
shape.
middle. I don't know. Like that's connected. I'm not sure I understand. You can say like, I like this idea sort of everything is kind of touching everything else, although it's not really that everything is touching everything else. Here all the vertices are touching another vertex, but they're somehow still in pieces. This is actually a hard question this is one of those times when the basic idea is kind of obvious, but to actually say what you mean when you say connected is not obvious. Actually, I think you can say it in terms of paths. That's my hint. Any ideas? The definition involves path, and it's kind of like what she said about everything is kind of connected to everything else, although. Any thoughts? In terms of paths.
Isn't broken.
Yeah. No path is broken. Something like that. I would say, like this one, for instance, in terms of paths, what makes it disconnected is sort of like you can't get from here to here, right? That's sort of what I want to say about paths in that graph. That's what makes it disconnected, is that there is no path from that vertex to that other vertex. Whereas in a connected, there always is a path from any vertex to any other. So that's the definition that I'm going to say here. This is not an obvious definition, although once I say it, I mean, I hope that it makes sense to everybody. A graph is connected when any vertex can be reached by a path from any other vertex. All right, that's the true definition of connected without using any words about pieces or anything like that. It's really all about paths in the graph. All right, it's not a hard definition, but it's not obvious how to come up with that as a basic concept. Okay, these are all basic terminology just so that we can start talking about examples of graphs. You can actually use graphs to model all kinds of real-world situations, all right? For example, let's try to imagine, I would like for us to kind of get used to thinking of a certain real world situation and imagining it in terms of graphs. This is something that kids do all the time, although usually you're trained to translate real world scenarios into equations or something and then solve for x. But I want to try and think about scenarios in terms of graphs. So let's, I'm going to do a bunch of examples in the basic heading of imagine a graph. There are many, many scenarios where you can translate some kind of situation into graphs. Okay, here's an example. How about each, imagine a graph in which each vertex is one of my kids. And their ages, I will tell you, are 3, 7, 12, 12, 18, and 19. This is totally made up. In real life, I have 2 kids. All right, let's imagine that these are my 6 kids, and these are their ages. And let's make a graph where, how about they, my kids, you know how kids are. Some of them are friendly with one another, and some of them are hostile towards one another. Let's say that they are friends with ones who are within 5 years of age difference. All right. The 19-year-old is not really friends with the 3-year-old because they're culturally too distant. All right. But let's imagine that each one is friends with one of the other ones if they are within 5 years of age difference from each other. Let's say 5 or less, then you can be friends. And anything more than that, they're not friends. All right? Can we represent this information using a graph? You want to try to understand, all right, among these 6 kids, who's going to be friends with who? All right? This is a nice situation to represent as a graph. Represent it as a graph. So I am going to let each of the kids be a vertex. There are 6 of them, and I'm going to connect by an edge the ones who are friends with each other. So I don't know how this is going to look eventually, but I will start with just 6 equally, arranged vertices. And I'm going to label them by those ages because each of these vertices represents one of the kids. And they are, I'll go around like this. 3, come on now. Sorry, my pen. I need a new tip on my pen here. 3, 7, 12, 12, 18, and 19, right? That's what I said. Okay, and now I'm going to make an edge for any 2 kids who are friends, according to the rule that I said before. So I will say each vertex is a kid, and then an edge connects friends, right? And the rule for friends is if you're within 5 or less, then you can be friends. So the 3 and the 7 can be friends. The 7 and the 12 can be friends. The 7 and the other 12 can be friends. All right. I'm trying to think of who can be friends with the 7 first. I'll draw in all those edges. So the 3, yes. The 2 12s, yes. The 7 and the 18, though, that's too much. So the 7 cannot be friends with the 18 or the 19. All right. And the 3 also, the 3 is not friends with anybody else. All right. How about the 12? The 12 is friends with the 7. We already saw. Not the 3. The 12 is friends with the other 12. Is the 12 friends with the 18? No, that's too much, right? That would be 6 apart. So this is all the friends for this 12. And also this is all the friends for this 12, right? There are no more edges for this 12. And then the 18 is friends with the 19, but I think nobody else. And the 19 is friends with the 18, but nobody else. All right? Great. This is the graph. What do you see about this graph? I mean, the graph, the point of drawing a graph like this is that it can give you some kind of insight that you might not notice just by looking at that like list of numbers up here. It's hard to visualize the relationships. But when I see the graph like this, actually I can visualize a whole lot of things. And it seems to me, for example, this is disconnected, which means that my kids will naturally like sort of segregate into two groups, right? There's the 18 and the 19, they will stick together. And then those other 4 will more or less stick together, although the 3 will always be kind of an outsider in that the 3 is only going to be friends with the 7 and not the 2 12s, all right? So the point is looking at the graph can tell you some important things or give you some insight. It's a good way of visualizing the scenario, all right? So this is disconnected, which is meaningful, right? The fact that this is disconnected means that my kids are likely to sort of naturally divide into 2 groups according to these 2 pieces of the graph, all right? I said before that the degree of a vertex is often meaningful. Can anyone say, like in simple language, what does the degree represent in this graph? For instance, the 7 has degree 3, but the 19 has degree only 1. What does that mean in terms of the who's friends with who or whatever?
Number of friends each one has.
Yeah, the degree represents how many friends each one's have. So the fact that the degree of the 7 is more than the degree of the 19, it means the 7 has more friends. The 7 has 3 friends, the 19 has only 1 friend. All right, so that's what the degree represents here. So I'll just say the degree represents the number of friends. Right? The degree is usually meaningful in these kinds of situations. All right, that's all I'm saying. I got a few more simple examples. How about, here's another one. Imagine a graph. This one is impossible to draw, at least on my screen. It's way too big. But let's consider the vertices are big-time Hollywood actors. Hollywood should be capitalized, I guess. All right. And then let's put an edge between 2 of them. An edge connects 2 who were in a movie together. All right. Imagine this graph. See you later. He's not into it. No, he's got to go somewhere. The vertices are Hollywood actors, and there's an edge connecting 2 actors who have been in a movie together. So I can't draw this whole graph just because there's, thousands of vertices in it. There's thousands? I don't know. There's a vertex for every Hollywood actor. There's probably thousands. And then there's an edge between some of them, right? But I can try to draw like a little picture. For example, here's Chris Evans, Captain America himself, and he's got, a lot of edges because he's been in some movies, right? One of those edges connects to Scarlett Johansson. Has an edge like that, right? And then Scarlett has, her own many edges like this to lots of other people. And Scarlett Johansson connects to Adam Driver. They were in that meme together, right? I never saw that movie. But. And I happen to know, at least I tried to look this up, I don't believe that Chris Evans and Adam Driver have been in a movie together. So there is, Adam Driver has a bunch of edges, but there isn't an edge. I would say there's no edge there. No edge here, all right? This is my read of the situation. Okay, so I can imagine this graph. Can we think about the properties that this graph might have? Now, you can't really draw the whole graph just because it's so big, but you can still think about it. For example, I could ask, what does the degree of a vertex represent? Any thoughts? The degree, remember, means how many edges are touching that vertex. How many people they've worked with? Yeah, this is what I would have said. The degree would be how many other actors they've been in a movie with, right? That's the number of. So this is the number of other actors they worked with. They appeared in a film with, right? So I could ask you, for example, who has the bigger degree? How about, say, Tom Hanks or Macaulay Culkin? Remember that guy? That was the kid in Home Alone who is now like a YouTube weirdo or something. He's very strange social media these days. What do you think? Who has bigger degree? It would be Tom Hanks as a more successful, longer career actor than Macaulay Culkin. No offense to Big Mac. It's Tom Hanks, right? Because he's been in more movies with more other people than Macaulay Culkin has. Right? Great. How about, here's another question. Is this graph connected? Any thoughts? This one I think is a little harder to ask, but is it connected? What that means is there a path from one actor to another through the graph? Like I could ask, is there a path from Tom Hanks to Macaulay Culkin in this graph? They are not connected directly, at least I don't think so. I don't think Tom Hanks and Macaulay Culkin were in a movie together. But can you get in the graph from Tom Hanks to Macaulay Culkin by going through a bunch of other people? I would say yes. I think you probably can. Off the top of my head, I don't know exactly how to do it, but yeah, there was a game that people used to play about Kevin Bacon. It's like a movie trivia game. I don't know if people do this anymore, but I remember when I was in high school, this was a big sort of pop culture trivia game. I say, all right, give me Tom Hanks to Kevin Bacon, and then your job is to name a sequence of movies. Tom Hanks was in this movie with somebody, and then they were in this movie with somebody, and they were in this movie with Kevin Bacon. Something like that. Anyway, I'm going to say, is it connected? I will say probably. At least mostly. It's hard to say for sure, but what it means to be connected is if you just choose any two actors, is it possible to get from one to the other by going through edges in the graph? And I think the answer is probably yes, although there might be. Is there like one person who is a big Hollywood actor, but they were never in a movie with anybody else? I cannot think of such a person. Although maybe it's possible in theory, but I don't think so. So I'm going to say, is it connected? Probably. That is to say, you can actually get from every actor to any other actor by going through edges in the graph. All right. How about this? Here's one last question about this particular graph. I happen to know. I looked this up. Britney Spears. Starred in one film. Anybody familiar with this movie? It's a film entitled Crossroads. I have not seen Crossroads, but Britney Spears was in Crossroads. All right. What does this mean about the degree of Britney Spears in this graph? What can you say about the degree? The degree, remember, means how many edges are touching Britney in the graph. Somebody said 1. Yeah, actually, the answer is not quite 1. One film, remember, the edges represent connections between actors. All right, so Britney has one edge going from her to every other actor who was in Crossroads. All right, so that's more than one. It's not a whole lot, but I'm going to say Britney Spears was in one film, which is Crossroads. So Britney's degree in the graph is, can I just say, it's small, like smaller than, Macaulay Culkin, because he was at least in a few different movies. Britney was only in one movie. Britney's degree is small. It is whatever, I will say, however many other people were in Crossroads, right? Which is not all that many. I mean, just one movie. However many people were in Crossroads, that would be the degree of Britney Spears. I suppose -1 because you don't count herself. All right. Great. I got 2 more of these examples because I want everybody to get used to the idea of thinking about real-world scenarios and then translating them into graphs. I hope that you feel like none of this is really very technically difficult. All right. How about this? Let's say a graph where each vertex is a Fairfield University student. Let's say a full-time student. Not studying abroad. All right. So you are part of this graph if you are a full-time student at Fairfield University. Each vertex is a full-time student not studying abroad, and an edge connects them. An edge connects 2 people who are in some class together. So inside this graph, all of you are connected to all of the other ones of you, but you are also connected to all the people in your other classes. All right, so this is the idea behind this graph. All right, can we ask some simple questions about this graph? How about what is your degree in the graph? Let's just say approximately. I suppose you could figure out if you really wanted to. What do you think? Is it like something like 5, something like 50, something like 100? What do you think? Can we say, is it something like 5? What do you think? Yes or no? I would say no, it's not like 5. Remember I said you are connected in the graph to everyone else who is in any of your classes. So in particular, you are automatically connected to everybody else in this room, and that's more than 5, right? Yeah. You'd say about 100. Yeah, you just have to think about how many people are there in all the classes that I'm in. Probably about 100. I don't know, if you're in 5 classes and there's like 20 students in each one, that's about 100. This is what I would guess your degree is. So I would say probably about 100. I don't know. This number it's the total number of people who are in some class with you, right? Which for most, if you're taking ordinary type 5 ordinary size classes, that's probably something like 100, right? That's the idea. This is your degree in the graph. It would include all the people in this class plus all of your other classes. What would you say to this? Is the graph connected? That means, can you get from you to anybody else in the graph by going along a path of students in this graph? Any thoughts? Yeah? Think probably yes? Yeah, I think the answer is probably yes. You have to just imagine, if you just take some random person, like some kid walks by, right now. Are you in the same class as that kid? Probably not. But is there some kind of chain of people in a class with somebody who's in a class with somebody who's in a class with somebody who eventually gets to that kid? Probably yes, I would say. If it were disconnected, that would mean somehow there were like some people who were just like in a separate universe or something as far as the classes they were taking, which I don't think is actually true at our dear university. So is the graph connected? I will say probably yes. It's not really, I mean, I can't say for sure. This is why I said, by the way, people who are not abroad, actually if you include abroad students, they would be disconnected from the rest of us here on campus because they are, you know, someone living in Japan for a semester is not in any classes together with anybody on campus here. And so they would not be connected to the rest of the graph. All right? Probably yes. Okay, I got one last example, and then we will talk about, well, some more examples, but one last example of this type. How about one more about Fairfield University students? Again, the vertices are Fairfield University students, and an edge connects two students if they are from the same state, United State. I will have to assume, I suppose, temporarily that everybody has a state that they're from. I know not everybody here is from the United States at all. But let's just say state. Or if you're not from the United States, you can have your state can be like a country or a United States territory if you're from Guam or something like that. Anyway, an edge connects two students if they're from the same state or from the same whatever else. All right. Here's a question. You have to know a little bit about our dear university, but let's consider two hypothetical people. How about Joe from Massachusetts versus, I try to think of a good California name, Sky from California. Who has the higher degree in the graph of Fairfield University students?
Joe.
I believe it's Joe, if you know something about Fairfield University. Joe has many other people who are from his same state. Those would all be edges in the graph. Whereas Sky from California would have fewer. There are more, because there are more people here from Massachusetts than California. So Joe has a higher degree, right, than Sky from California. All right. She goes to the beach when she's home. Joe, I don't know, goes to the bar. I don't know what people in Massachusetts are known for. All right. What about, is this one connected? For example, can you get from Joe to Sky in the graph by doing edge by edge? I think the answer is no. All of the edges that Joe is connected to are other people from Massachusetts, and you can't get from somebody in the Massachusetts clump into somebody from the California clump. So the answer here is no. Actually, there will be pieces of the graph for each different state. Each different state has its own region in the graph that are all disconnected from one another. Actually, those are called components. So this graph has a different component, is the word. A different component for each state. Right? So there are a lot of people from Massachusetts, so the Massachusetts component is fairly big. A lot from Connecticut and so on. Not so many from, Washington State, something like that. All right. I'm trying to give you a lot of different scenarios that you can imagine in terms of graphs. Any thoughts about any of that? All right, I have a few more so you can expect some homework questions like this. I will just describe some kind of scenario and say, ask you to imagine that making a graph out of this, and then something about what's the meaning of the degrees, what's the meaning of is it connected or not, that kind of a thing. All right? Graphs are very, very useful in real-world mathematics. So I will say super useful in the real world. It's kind of, in my opinion, a bit scandalous that we don't teach high school students any graph theory. Typically, I don't know if you've ever seen this before, but because it is so useful in the real world, I would say probably more useful than things like trigonometry, which we teach a lot of kids in high school. Graph theory is super useful. It turns out not to be terribly useful in physics or like chemistry, which is what most of our math in school is preparing people to do that kind of science. But anyway, I'm going to try to give you a whole bunch of scenarios in which graph theory is super useful in the real world. How about road navigation? Like when you ask the lady on Google Maps to tell you how to get from here to there. Basically, what that lady is doing, I refer to my GPS as the lady. What the lady is doing is she has in her mind a massive graph of every street and every intersection between those streets. And when you say, I want to get from here to here, she figures out the best path from here to here in that graph. So the giant road networks look like graphs, right? And I will say the GPS lady, or man, or whatever, the GPS lady is finding the shortest path from one location to another. Usually the shortest path. Although shortest to the GPS lady doesn't always mean shortest in terms of mileage. It might mean shortest in terms of the time it takes if you factor in, traffic and whatever. So the GPS lady is finding shortest paths from one point to another. So if you somehow were privy to the way they actually do this business in the computers at Google or at whatever it is, they are doing a lot of graph theory pathfinding computations, right? This is super big business in the real world. How about similar kind of thing? Airline routes. Airline routes are typically like, you've probably seen a picture describing where the flights go. There'll be like a map. This is a map of the United States, obviously. And you can see like maps that look like this, which means sort of this is where all the flights go from here to here to here, right? That map really is representing a graph. And something that's interesting about these routes here, this sort of network of routes is expressed as a graph. And these lines that are on the graph are not actually exactly where the airplane flies. Like when they show you a map like this, they're not actually saying that the airplane actually follows this precise line when it flies. The plane, to ordinary people, it doesn't matter exactly what path the plane takes. All that's important is that there is an edge here. That means there is a flight from here to here, all right? So these lines, they don't actually represent where the plane flies specifically, like geographically speaking. They represent the fact that there is a flight that goes from here to here. But, it roughly follows the line probably, but not necessarily. All right, so this is expressed as a graph. And in this case, the high degrees, if you have a vertex of high degree, these would represent, what would that represent? A high degree vertex versus a low degree vertex in a graph like this?
Many different paths.
Yeah, it represents how many different flights are going out of that city or whatever. This would roughly represent how big the airplane is, or how big the airport is, right? A city which has only one edge coming out of it means they've only got one flight. They're probably a small airport. So high degrees represent, in the business, they represent like airline hubs is what they call it. And the airlines actually care a lot about graphs and paths also. This is why each airline has decided to make certain cities into their hubs. I don't know if you know much about the way airports are organized, but they intentionally they choose a few cities to have tons of flights from, and then all the other cities get like one or two. This is generally how the airline business goes. And the reason they decided to do that is because of some kind of optimization to the routes in this graph. All right. What else? I got just a few more of these. How about computer networks? The best way to visualize a computer network is in terms of graphs, where I have, a bunch of different vertices, and then some of those computers are connected up just like in some random way. Computers are connected with one another, all right? What we have is like the internet is basically composed of millions of individual computers that are all communicating with one another, not directly, but through different sort of hops along the graph. Like if I send an email to you, the email doesn't go directly from my computer straight to yours. It bounces through a bunch of different, servers or whatever. And the correct way to visualize this picture is by graphs like this. So in this graph, I would say this looks like some kind of server because it has a lot of connections, whereas this is maybe like somebody's Xbox or something, which only connects to one thing, like your home Wi-Fi or whatever, and then it patches eventually into the rest of the internet. All right. The way that we think about computer networks is always in terms of graphs. And again, these graphs, they do represent connections, but they don't necessarily mean that there is like a straight line wire going from one computer to another. The wires essentially never go in a straight line. They're wiggly, even though I drew these lines as straight. All right. And all right, just one more, and then maybe that'll do us for today. My goal for today is just to explain to you, convince you that graph theory is super important and comes up all the time in the real world. How about social networks? Most social networks, I'm talking about things like, Facebook, Twitter, Instagram, whatever, those kinds of things. Most social networks can be described using graphs, and that is the proper mathematical way to analyze. If you wanted to do some kind of statistical analysis of Twitter or Facebook or something, you would think of it in terms of graphs. So I would say in a typical social network, each user is a vertex, and then they are connected, like for instance on Facebook, each user is connected to the people that it's friends with on Facebook, right? Or on Twitter, I would be connected to all the people that I follow on Twitter. So each user is a vertex, and then relationships, by which I mean like following on Twitter, or like Facebook friends, or like on YouTube subscribers, right? Any of that stuff. I don't use a lot of social media myself. But anyway, each user is a vertex, and then all of those individual relationships are edges, right? On the graph. And you can ask all the usual questions about what does degree represent in a social network? Somebody with a high degree versus somebody with a low degree. Somebody with a low degree means they have very few connections, which means like they don't have a lot of friends, or they don't follow a lot of people, or not a lot of people follow them. So degree represents sort of the number of friends or followers or whatever on whatever social network it is. All right? Super important. If you want to analyze a social network, a real-life social network, which a lot of people do, there are a lot of people who study these things. You've got to do it in terms of graphs. All right, graphs are important, and graphs are kind of everywhere. I would say they come up more often in like human constructed scenarios. Everything that I've mentioned here is all about sort of sociological constructs, human constructs, rather than things like the laws of physics are basically expressed in terms of equations and like calculus. But sort of the laws of human interactions or man-made things tend to be expressed in graph theory as the fundamental like framework by which you analyze these things. All right, I think that'll do it for today. Next time we'll get down to some much more specific mathy stuff.